What our group wanted to figure out was how the amount of charge that we give to two balloons could be measured. Our experiment focused on how to accurately measure charges of a balloon. We decided a way to go about this by using two balloons, each with their own charges, to set up a procedure to help us solve this question.
For our experiment, we needed a balloon pump to get the balloons to the same size, a large piece of fabric to charge the balloons, a digital scale to record the data that would help give us an insight on the needed information associated with electrical forces, therefore the charge of the balloons, a tape measure to keep track of the distance between the balloons, and a camera to record the data in a way that we believe to be most accurate.
For our procedure, we pumped the balloon up with 30 pumps each to assume that they're roughly the same size. We rubbed them individually with fabric for the same amount of time, and then we set one on the scale, zeroed the scale, and brought the other one towards it while taking pictures at different distances apart. We then discharged the balloons with our hands and repeated 3 more times. In this system schema, we only included relevant interactions as shown in our free body diagram. Balloon 1 in this case is the balloon touching the scale, and balloon 2 is being pushed towards it, and since we are holding balloon 2, it is a fixed charge. After we placed balloon 1 on the scale, we zeroed the scale, so the only force that impacted the scale reading should have been the electric force of repulsion between the two individually charged balloons that was shown through the normal force exerted upward.
Newton's third law is for every action there is an equal and opposite reaction. This law helps explain why we're able to measure the normal force through our experiment. The two like-charged balloons repulse away from one another. However, the balloon on the scale cannot move away and applies a force on the scale. The scale applies an equal and opposite force back on the balloon, which can be measured and seen through the scale reading. Since we charge the balloons the same way, we expect them to have the same like charge, which means there will be a repulsion. And the Coulombic attraction helps explain why there will be an increase in the scale reading as we push the balloons closer together. The distance shown above each image is the measured distance between the two balloons centered. As seen in the pictures above from trial 1, the scale reading increases as the distance decreases. This shows the repulsion of the two like forces increases. The scale is responding to the repulsion force with an equal and opposite normal force, as shown on the scale. Our second trial was similar to our first trial. We observed that as the distance between the balloons decrease, the Coulombic repulsion increases.
The fact that this trial did not follow the trend is instructive. Note that the two balloons are not perfectly aligned in the last image. This would decrease repulsion. Though the other trials followed the expected trend, some variability in the calculated force may be explained by the relative positioning of the balloons. Here, in our fourth trial, we also have an outlier of our data.
Here you can see how we took each position photo and turned it into a charge value. We took the displacement in inches and converted it to meters. We took the scale reading in grams and then converted it to kilograms and then newtons. And then we used Coulomb's constant and rearranged the electric force equation to get Q. So when those calculations were done for all of the different images shown before, I took an average value for each individual trial set. When you look overall, it shows that the charge of the balloon was between 0.08 and 0.125 microcoulombs using the procedure we implemented. So how long we rubbed it with the cloth and how big we made the balloons. In trials 3 and 4, I excluded the positions that were clearly off-center as shown by the previous slides. So in conclusion, our physics models held, which means that our model overall held. Coulombic repulsion increased as the balloons were brought closer, except for the couple points mentioned, and the consistency in the calculated values seems to suggest that our model is fairly accurate. Some limitations of this is that the balloons aren't really evenly charged, then the calculation that we made isn't exactly accurate. So replacing the held balloon with an object with a precise known charge, like something that generated a selected charge, would be better. Some sources of error come from our assumptions. We assumed the charged balloons were point charges that were evenly distributed, and if rubbing wasn't done completely evenly and discharging wasn't done evenly, the charges of the balloons would vary from trial to trial. And as we saw earlier, not keeping them centered over each other would cause calculation issues as well. So all these things that could be improved upon and controlled and regulated more closely to get a better result.